For this experiment, we are going to explore gas law, specifically Gay-Lussac's law, where basically as temperature increases, the pressure of a gas will also increase. If the temperature goes down or as the gas cools, you're also going to have a decrease in pressure. So we're actually going to be using a hard-boiled egg. We're going to leave it here on the neck of this craft container. What we're going to end up doing is we're actually going to be lighting up this match, place it in here, and then watch what will happen to the egg once the flame dies down. What's going to happen is the outside pressure is going to push the egg inside. So let's check it out. So the materials that we're going to be using is this craft container right here, matches. We have our hard-boiled egg right here. Now, if you look at this craft, I do have a small piece of tissue here that's soaked in a little bit of alcohol just to allow some flames. And then place the egg right there. Notice how it sucks the egg inside the craft. Now, if we wanted to remove the egg out of this craft without damaging it, we can always flip the egg upside down like this, okay? And try to get it as close as we can to the brim. Again, we don't want to damage the egg. And then what we can do is we can actually heat this jar. What we're going to do is we're just going to let this sit here, allow the gas that's inside the craft to heat up, causing the pressure to rise. And once that pressure rises, we're going to see the egg get pushed out of this craft. Let's do a quick checkpoint here and see where our egg's at and see if it'll just come right out of the neck of this craft. And what do you notice? The egg just came right out. It was stuck at the neck, but as I flipped it over, it came right out. The pressure is causing the egg to come out of the craft, and that is why we're able to remove the egg the way we did.
I'm gonna spin a matchstick that is on top of 2 nickels and underneath a cup. For this experiment, we need 2 nickels, a matchstick, a balloon, a cup, and that's it. Now what we're gonna do is we're gonna set up our experiment. First, you take 1 nickel and place it down onto the table, and then you take your other nickel and you try and balance it. Let's see if I can do this. It may take just a second to get it done, but it's a pretty cool experiment whenever we get it all done. Come on, boy. So hard to balance. Come on, boy. Aha. Now what I'm gonna do on this, now that Brooks has it assembled, what I'm gonna do is I'm gonna rub my hair and we're gonna see what happens. Okay. Our negatively charged balloon repels the electrons from the match and attracts the match's protons. When a neutrally charged object is light enough, like our match, a negatively charged object will attract it. Now you need to reduce the amount of friction on the match for this experiment to work. And that is why you balance the match on top of the nickel. Balancing the match creates less surface area affected by friction and allows the match to rotate. I'm going to teach you how to balance a fork and a spoon on a toothpick. Let's get started. First, let's grab our materials. We need a spoon, a fork, a toothpick, some matches, and a cup. Pretty simple, right? Now I'm going to hand it off to my assistant, Brooks.
Thanks, Glenn. Okay, I'm going to show y'all today how we're going to balance this fork and this spoon on a toothpick on a jar. Let's get started. So first, we're gonna take our fork and our spoon and we're gonna merge them together like so. That's the quickest I have ever done that. One last material we're gonna need are some matches. So we're going to take our match. We're gonna light both ends of the toothpick.
5 minutes later.
Okay, what we're looking for, see how, despite the toothpick getting burned right to its very, very edges, the fork and the spoon are still balanced. Now we're gonna have Glenn explain why that is, but this is what I want you to be looking at. See how there's no space, there's no room on the toothpick for it to be balancing, yet it's still standing strong. How is that possible?
What we did there was find the center of gravity between the toothpick and the silverware. The center of gravity in the balancing fork and spoon is directly below the spot where the toothpick rests on the rim of the glass. You'll notice that the handles are curved directly below the toothpick. This actually moves the center of gravity directly below where the toothpick rests on the rim. Now, when Brooks burned the toothpick, why didn't the flame keep burning and knock over the utensils? Fire requires 3 things. It requires heat, fuel, and oxygen. You take away one of these, and the fire goes out. The fuel and oxygen were there, but you took away the heat. The glass and the metal took away the heat, and the flame went out. But as you saw, the fork and the spoon remained balanced because the center of gravity didn't change.
Science is all around us, including in the kitchen.
So today we're going to be making spherical balls out of juice. Very similar to what you probably see with boba balls, as well as some of the toppings for frozen yogurt, I believe.
Yes, exactly. So what we're gonna need to do that today is some sodium alginate.
And calcium chloride.
So first thing we're gonna do is we're gonna take some calcium chloride.
And mix it with a cup of water.
We're gonna go ahead and mix it in. As he's mixing it, let me go ahead and explain how this works. Think of sodium alginate as a string of molecules. As the molecules are kind of sitting in a soupy liquid, they bind to the juice. Then what we're gonna do is we're gonna mix it together with the calcium. That calcium goes ahead and closes up the molecules and it makes a bubble. So this time we're going to go ahead and do it with some Dr. Pepper. Add the sodium alginate. Now with soda, this is gonna foam a little bit more. So we're gonna mix it up. Then pour the rest in. So whenever we mix the sodium alginate into the Dr. Pepper, the long molecule chains that are in the sodium alginate, they're picking up the Dr. Pepper and they're trying to latch onto it. That way, when we add the calcium, it's going to pick up and become gelatin.
Yeah.
Oops. Now we're just going to pour it in. That just stringed out. Look at that. That's so cool. It's like a little snake. I'll try and make some droplets this time. That one formed immediately.
Here we go.
There we go. And I think it takes a minute to form.
Yeah.
So it's been about a minute, and I feel confident to use my hands this time. How do you feel?
Let's do it.
All right, cool. Ready? 3, 2, 1. Oh, they're really jello. Look at that.
That is amazing.
Three, 2, 1.
Tastes like Dr. Pepper.
Tastes like Dr. Pepper. Let me pull out this giant snake that we got here.
Yeah.
Look at the giant snake. The Dr. Pepper snake. Look at this.
That's awesome.
The Gucci fall
Yeah.
line. You wear it around your neck.
Or use it as a cake topper or something.
Exactly. This would actually be a pretty cool cake topper.
Yeah.
I'm ready?
Yeah.
3, 2, 1.
Yeah.
Tastes like Dr. Pepper.
Yeah.
Oh, it's actually delicious. Really dark color. And all it is really just the juice collected by the sodium alginate and the calcium chloride. So whenever you have sodium alginate and it gets calcium, it essentially traps the juice inside, kind of like a little bubble. And it's completely safe to eat.
Not bad.
Yum.